All right, happy Monday. How's everybody doing today? So, I'll start off with the announcements that you guys have probably already figured out that I'm behind on the My Open Math stuff pretty badly. Uh, right, if you were waiting on the homework 3, I'm not sure when I'm going to have that up realistically. So, I was explaining to some people in class that I was trying, the whole point of this is to get it to auto grade and stuff. And so I thought I had this clever idea of doing check boxes, and I've obviously been using AI, and I haven't gotten it to work yet, the auto grading and all. And obviously I could do them as a written submission, but that's not the point of the project. It's I'm trying to eliminate all the manual hand grading and trying to fix, because I work with other platforms too, and it's different auto grading issues depending on the platform, yada, yada, yada. So that's the point of that, is to get rid of all this, but because of that, I'm super behind. And then, so I'll just say, maybe I'll try to be a little faster and at least do something with the My Open Math. But otherwise, just refer to any other copies. Since, like I said, this project is a large project. And so far, it's just me. In addition to grading 100 students, which is a large task in itself. Yeah, so same thing with chapter 4. So I don't know how well chapter 4 will be with My Open Math. I haven't played with some of the chemistry tools that are on there, whether that'll work. So it takes time for me to get creative with it. So we might just have to do. Oh, and then so the other issue. I know you guys just have issues, the class. Well, it's because we're doing the switch over. So you guys got caught in the switch over year. So I'll just put paper blackboard probably for those. It's going to take me too long to get too creative with that. But the My Open Math will obviously work a lot better with math type style things. So I think once we get past this, I'd have to look at our syllabus. And so speaking of that, I always hit the Xbox. So speaking of that, we should look at your syllabus, yeah.
So I should just do last week and this week on Blackboard.
Probably, or paper. I'll try, like I said, I'll try to do something, at least with the naming. I can maybe throw up something, but I'm having trouble, obviously with anything geometry, drawing. And eventually I might have to give up and just do those as manual grade, even with the My Open Math, but I'm not there yet in the exploration process. But I don't want to hold up your progress. But on that note, we're coming to the midterm, so we should just look at that. So the weeks are flying by. So we're finishing up our last chapter. So we're going to do covalent compounds today and a little bit of geometry. So that's what that handout is for. But then next week's already our exam. So if you're in person, kind of the thought is we'll use a Monday in class to review, right, during our normal class time. And then you'll have all of Wednesday to take the exam. And I guess I'll make both versions available, if you wanted to do the online version. I'm not totally averse to that, but I'm probably not going to make it in My Open Math version since, right, I'm still, I got all your messages about all the bugs, but I haven't gone back yet and fixed them all, so there's still a lot of work, so I'm not going to do a My Open Math exam, but either a Blackboard exam or an in-person paper exam. And so again, that will be on Wednesday. And if anybody wanted to do testing center things, just make sure you get that in as well, so we can figure that out. So I haven't heard anything of anybody who wants to do alternative testing, but time accommodations should be in Blackboard. If they're not, I'll fix that and message me about that. I don't think I have any accommodations in class, but again, we can do that in class. That's not a big deal.
And that's the midterm exam?
Yeah. And then the lab practicum is only for the online people, so we're not going to have a lab practicum right in here. We'll just do a regular lab, so that's not on the schedule, but we're just going to meet regularly. Or maybe I'm looking at the wrong syllabus. No, this is supposed to be yours, but I must have something wrong in there. But yeah, we'll just have lab on Wednesday like we normally do, right? Wednesday morning, meet for lab. And so that will be fine. And then, so once we get past the midterm to kind of the My Open Math, hopefully should function better because this is more math stuff, and that's obviously what My Open Math is much better at as opposed to trying to do chemistry stuff. But I'll still play with it. All right, so that's where we're headed. And then during the break, I'll get more copies of the lab because this week's lab is pretty fun. It's just rather long, but it'll be a good one. Other questions, comments? Oh, no, I do have stuff graded, so I'll get that back to you. I think I'm still missing a few reconciling. I was going through the grade book this morning, but I don't think I quite finished transferring everything from the My Open Math to Blackboard. So, yeah, give me another day, and then if by Wednesday I still don't have things fixed, then you guys can start pinging me with more emails of what I've missed. All right, so let's look at covalent bonding then today. So like we kind of teased at earlier, is now when we have two atoms that share one pair of electrons, that's called our single covalent bond. And so we looked at water earlier, so we'll look at water again. And again, starting with its Lewis dot structure. So telling us that oxygen likes to make two bonds. And so then when hydrogen comes along with its one electron, right, it makes our covalent bond. And so they've represented it by two dots. And then I'll redraw it as the two dots equal one line there. Then I'll draw in our valence electrons. Did you have a question? Oh, sorry. So give people a second to copy that. And so that's something that we want to kind of practice doing, is keeping track of electrons. You can already start to see from this one, right, oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6. Each hydrogen brought 1, so 7, 8. And then in either one of these representations, right, here, of course, they're all drawn explicitly. So there's the 8, and then I'll kind of re-highlight what they've already shown us. But they have this oxygen right in the center, so it's feeling those 8. So 1, 2, 3, 4, 5, 6, 7, 8. So again, kind of proving, okay, that's satisfied now by the octet rule. And then we have hydrogen here, so feeling those two, or again, kind of drawn down here in this single bond representation. Again, there's 2 electrons, so satisfied by the duet rule since it's on right the first shell, so it only needs to fill the 1s orbital there. And then of course other hydrogen looks the same. Other questions? And so then we could have a situation where 2 atoms share 2 pairs of electrons. And so that could be in the case of oxygen in the diatomic. And again, right, think back to the Lewis dot structure. There's our hint. Okay, well, it likes to make 2 bonds. So that makes sense that, right, if it bonds with itself, it's going to make 2 bonds there. So I'll redraw it like so. And again, right, most important thing here is just keeping track of electrons. So 6 valence electrons for each times 2, so we should have 12 in our system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that checks out, right? Either representation, you look at it. And then I'll show, so it also mentions that it can double bond with other elements. So again, these are like important in your body and other biologicals or drugs, of course. And so we'll just draw out formate. So just a simple oxygen, again, double bond it now to carbon, put those 2 lone pairs, we don't want to forget those. So again, octet rule, and then these carbons would be bonded to hydrogen there. And then again, nitrogen can kind of do the same thing. And then we can also see triple bonds. And so we're just going to go over single, double, triple. I think technically you can also have like quadruple bonds. I don't know if there's formally like 5 bonds, but those are, again, like more esoteric research instances. So we're not going to focus on that, but of course you could kind of extrapolate. But we'll look at our triple bond. So again, this is our last kind of common bond we'll see, where now we have 3 pairs of electrons giving us 6 electrons total between our atoms. And so nitrogen, so again, reminding yourself, okay, yeah, one of those diatomic elements, again, just found in the elemental form, like N2. So now we have our triple bond. And I kind of criticize how they draw it here just because that looks funny. Anyways. So we have our 3 bonds in the middle, so 3 times 2 is 6. And again, you can highlight octet rule satisfied. Then our next one, right, octet rule satisfied. So both 8. And then as we go down, the trend tends to be that they get shorter. So, right, our single bonds tend to be our longest and also weakest. Again, in general, right, comparing between single, double, triple. It obviously also depends on like what 2 atoms they are. And so double bond would kind of be in the middle. And then our triple bond should be our shortest and strongest bonds. Again, just kind of general trends there. And then we can also potentially see, so you have like a carbon, nitrogen triple bond, right? That can also happen. And sometimes, again, some like triple bonding. All right, so let's look at some examples. And so now let's just start with kind of our typical compounds, typical covalent compounds. And so our classic one for group 4, so if you remember, right, we kind of learned that carbon has this special Lewis dot structure. And so what this is getting at is carbon's tendency to form 4 bonds. And it also tends to do what's called sp3 hybridization, but that's kind of almost like beyond this class. Like, yeah, maybe you want to be somewhat familiar with it, but we're not going to get like too deep into MO theory. So then methane is our classic example, and I'm trying to draw it in kind of the 3D form here. So we have our carbon and these 2 hydrogens in the plane of the board, and then this fattened wedge is coming out towards us, so out of the plane of the board. Yeah, so it's kind of pyramid, or really we want to call it tetrahedral, But yeah, it does kind of have, right, that pyramid base there, exactly, and save your pyramid thoughts for another geometry. But again, the tetrahedral for the 4 shape. And so recall diamond is also in that structure, but with carbons here, right? So it's carbon, carbon, carbon everywhere with that repeating tetrahedral structure. And then the other thing to note is that our other group 4 compounds also tend to do this. So we'll do some examples. So that's going to be, let's get my pen color. So we have silicon. I'll just put tetrachloride, but there's also technically all the other variations of all. The fluoride is probably too toxic because that would give off like HF gas, so that'd be terrible. So these compounds react with like water in the atmosphere. So you have silicon tetrachloride, silicon tetrabromide. I'm sure the silicon iodide also exists, but probably just not synthetically as available. And we should put all our dots on here. Again, just showing that our chlorine has 7 valence electrons, right? Still wants to make 1 bond. So of course 1 is involved in bonding. Try to draw my geometry. So just filling in my electrons there. You could again do your total electron count. So we have 4 valence electrons, right, from silicon, plus now 7 from each chlorine. And there's 4 of them. So then we should have 32 electrons total. And then just, again, kind of sanity check yourself. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 4, okay, 32. So that looks good. So you just want to make sure your structure kind of matches there.
So the line between silicon and chlorine is like, it symbolizes 2 valence electrons.
Yeah, so that's, again, 2 valence electrons, and we're looking at a normal bond where each one is contributing 1 electron. We won't get into data bonds right now. All right, so now let's look at our group 5 kind of typical structures. And so for these, we can think about, again, our group 5 Lewis dot structure. So let's start with nitrogen. So it has kind of 2 lone pairs at the top, and then 1, 2, 3. And so there's a lot of hints, again, that this Lewis dot structure shows. So we have our, right, 3 lone electrons here. So again, kind of hinting that it wants to make 3 bonds. Although that being said, these electrons can go on and attack other things, but we're kind of not there yet. But these electrons do stuff. They're not innocent. But let's just start with ammonia. So that's our typical representative compound. And so it should look similar, right, to tetrahedral. It's just we replaced one of the hydrogens with 2 electrons there. And then, so other compounds, so phosphine then also looks like this, with, again, our hydrides formerly. So like I said, they can also go on to form, we'll kind of look at the hypervalent structures in a second, but again, looking at these lone pairs and kind of hinting at the reactivity. So all these things are reactive with oxygen, but especially phosphines. So they really love that phosphine-oxygen bond. So then it'll quickly react with oxygen to make this double bond like we've seen before. So going back to what we were just saying, oh yeah, oxygen and other organics, or kind of these main group elements you'll find, again, form these double bonds there. And then there can be, of course, other variations. So I just showed the hydrogen version, but there can also be chlorides. So PCl3 is a pretty common compound that's used in like main group starting materials. Again, it's going to be nasty, water reactive because of the same phosphorus double bond issue. And then, of course, arsenic, right, just going down the row would exhibit similar properties and make similar compounds. And so again, right, that's the point. It's like, okay, this should start to look repetitive. Yes, they're in their same like columns, aka their families, right? So they all have similar reactivities. That's how they kind of discovered them as well, right? So they're mining these things. They're trying to figure out what's what. And so they're comparing these similar compounds that they make. Oops. All right, so let's keep looking at, again, kind of our basic compounds. So we saw oxygen. So I'll just rewrite it for us of group 6 again, that they first kind of typically make 2 bonds. So lots of examples of that. Just again redrawing oxygen out here. Oh, forgot my charger. And then we also have, of course, water. And then we could also have, of course, right, our heavier analogs of group 6. So sulfur dihydride, selenium dihydride here. And then, so you guys know of CO, right? So carbon dioxide, or 2 oxygens. You guys, you probably wouldn't be familiar with CS2, or carbon disulfide. But you can now guess why carbon disulfide is a toxic compound. And so the problem with carbon disulfide, well, there's really 2 little issues here. And so, of course, you can appreciate, right, your body expels CO2. And you know you have hemoglobin, right, which is iron base, circulates around your body. And part of the equilibrium process, right, is it gives off our CO2. Well, the problem with CS2 is sulfur binds more tightly. So not only is it a heavier gas, right, since of course sulfur is down below in the periodic table, so a little bit heavier, but now it binds a little more tighter too to your hemoglobin, so it's harder to release it. So that can be toxic, yeah.
Why does it bind tighter? I don't know if I caught.
It's probably just the thermodynamics of it. It's just the iron-sulfur bond is more favorable. So like I said, that probably goes down to like a thermodynamic argument at that point. But yeah, so then if you're exposed to this, which I've seen firsthand because my lab mate was exposed to this, so you got to go to the hospital, right, get your blood monitored and all that, like your oxygen level. But then she did kind of feel like the side effects manifest as like drunkenness or like the headache. So yeah, she definitely kind of had this weird hungover feeling kind of. And then, again, the heavier analogs would also exist, but not familiar with this compound in practice. So, and then group 7, so we saw our halogens. And so they typically, again, make 1 bond, but we'll look at kind of other exceptions. So we have, right, all our diatomics, if you recall, right, fluorine, chlorine, bromine, iodine. So they would all be similar. So, okay, they all share a single covalent bond. So I'll just kind of draw most of them out. And then any of our acids as well, so like HF, we could draw like so. Again, just appreciating one covalent bond, or going back to like the silicon tetrafluoride, tetrachloride compounds. So I'll just kind of redraw them. But now we're looking again at the chlorine and appreciating that they just make one bond here. And I'll fill in all the electrons for fun. And so again, make sure you grab the Compound Chem cheat sheet, because that's pretty useful for that, just to help you with the geometries. And so again, right, I'm not trying to test you on memorization, so that's why I refer to your geometry sheet. We're only going to be like tested over a few of the main geometries as well, so we'll re-go over that, but so you're not expected to like know everything all inclusive. All right, so let's now look at kind of our, I'll call them expanded octets, but they're also like our funky scenarios. And so the thing to note as well is, well, let's look at, actually, so like I said, I think I got sidetracked, total ADD. So you're also caught in this, I keep calling things chapter 3, chapter 4, but I'm really referring to a book that you don't use. And so you're using officially, because like I said, we're trying to switch over to all OpenStax. So officially you have this book, but a chemistry book is a chemistry book, so it really doesn't matter, especially at the 100 level. But then most of your stuff is going to be, sorry, I clicked the wrong chapter, kind of this chapter 7. You have covalent bonding in chapter 7, and where else am I looking for? So I was looking for, oh, that's too much. Well, no, sorry, I thought I pulled it up. Oh, probably this chapter 7.6, molecular structure and polarity. So that's kind of your reference point for that. But like I said, more things that I was supposed to build in my open math. But that's where these class notes are like super useful. So like everything in class, right, I'm just trying to give you everything you're going to be tested on. So that being said, I haven't looked at your book enough to see if it says what these books sometimes say. So I was trying to find it. Blah, blah, blah. Oh, well. Well, I don't know if your current book says it, but many books say this. And so when you get to these expanded octets, sometimes your book will have this line of like, oh, blah, blah, blah. They are able to go to the expanded octets because they invoke d orbitals. But they actually do not invoke d orbitals. So that's the first thing I'm going to say. So do not invoke d orbitals. And so we won't go down like the full rabbit hole of why this is, because that gets into like a molecular orbital theory argument, which, I mean, I would be excited to get into, but no one would understand, and that's like way too beyond the level of this class. But I just want you to understand that is, okay, we're not invoking any d orbitals. really our p orbitals are sufficient, and they are in enough places physically that they can do these expanded octets. But like I said, I won't prove that in here. I'm happy to chat like after class about that. That's definitely an after class, outside of class topic, but otherwise it's irrelevant for this class. All right, so going back to what we do need to know. So again, we're just appreciating that some of our noble gases that we had said were mainly inert can form compounds. And so the two typical ones are either xenon difluoride or xenon tetrafluoride. And so both of those, again, xenon ends up being formally hypervalent. So I'll draw out our structure. So xenon, 8 valence electrons. So now 2 are going to go to bonding. And then that leaves 1, 2, 3, 4, 5, 6 as these kind of lone pairs there, not involved in bonding. And of course we have our non-bonding F electrons. I'm just filling those in. So it would look like this. So this would be linear. So just a line. And so again, some of the explanation for why that is xenon is very large. So it's got a diffuse orbital. And so notice it's also with fluorine, right? So very electronegative element. So fluorine really wants electrons. And so again, that's what a chemist does, try to make new bonds and force new compounds. And so they did. And then you can also do the same and make xenon tetrafluoride. And so this is going to be a square planar structure. I'm not the greatest artist. And so we have these 4 are in a plane, so everything's in a plane. And then we would have 2 lone pairs of electrons. So again, 8 total electrons, 1, 2, 3, 4 involved in bonding, 1, 2 non-bonding. So I'll draw in my fluorines. And again, let's not forget to do our total electron count. So again, xenon should have more than 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll put, right, xenon kind of feels 10 electrons, or it has a total electron count of 10. And then now let's count it for this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for that one. So 12 valence electron, or total electrons, let's say that. 12 total electrons again on xenon. So again, why we say it's called hypervalent, since we have more than the octet rule. I keep just like clicking random stuff. I apologize. All right, other questions? All right, let's look at a few.
Wait, these are called hypervalent, you said?
Yeah, either hypervalent or expanded octet, since they have, again, more than our expected number.
We're going to say here more than 8.
Yeah, so more than 8, like total electrons on the atom is how the analysis is considered. So let's look at a few more kind of expanded octet examples. And so again, this goes back to like another erroneous thing that goes back to the d orbitals of the like, oh, we can't invoke d orbitals because the second row doesn't do this. And so I think I mentioned this with neon. I'll make the argument again with now nitrogen. So all this is to say, well, PF5 exists, if I could write that out correctly. So phosphorus pentafluoride. And so we're kind of hinting at our naming, as you can tell, but we'll formally go over it. So 5 fluorines on there, so phosphorus pentachloride, right? So earlier we also had phosphorus trichloride, or phosphine, or any of those phosphorus with 3 things attached to it. Well, now we could go ahead and force it to have 5. And I'll try to draw out, at least kind of poorly, what our structure looks like. So this would be a trigonal bipyramidal, or bipyramidal, however you want to pronounce that structure. And so you can kind of see why, right? We have like triangle in the center and then 2 pyramids. So I'll fill in our electrons now. And so just a reminder that NF5, right, it doesn't exist because of a geometry argument. So too small, but again, nothing to do with the lack of d orbitals. So it could do it, right? It has p orbitals to totally invoke, except if this molecule, were to exist, and I apologize, like I said, I can't draw, it would have to have, they've done calculations on this, so it would have to have an elongated phosphorus bond here, and so it just doesn't work out. I kind of drew that a little exaggerated, but like I said, so it's not a stable compound since they just can't physically fit in all those fluorines around. Otherwise, again, it would be able to form, so it's just too small. But other variations do exist. So, for example, like arsenic, pentabromide, and again, it would look similar. So arsenic in the center, our trigonal bipyramidal geometry. I forgot to talk about your compound chem Vesper sheet and kind of how to read it. So let me pull it up for a second. So like I said, you can probably just highlight a few of the key ones, right? So looking at like linear here, but here's how to read it. So we have this key here, and so your key starts off with like how many things are attached to it. So that's either going to be lone pairs, so right, two electrons paired together, or an atom. So right, this is just like how many things are attached to the center. So again, lone pairs or atoms. And then you have, so of course if there's 2, it's obviously linear. But now let's look at 3, for instance, right? So 3, and so we have 3 BP, which means 3 bonding pairs, or the pictures are good, right? Because it's showing you it's bonded to 3 things. And so that gives you a trigonal planar geometry. And so this will probably be one of the ones you have to know. But then, so we won't look at this one, like I said, in a test, but we'll at least appreciate it now. And so if we move on over, this is a situation where we have 2 bonding pairs, right? So 2 atoms, but then 1 lone pair with the little dots swapped in. And so that would give us a bent geometry. And then when you're using this, it doesn't matter whether this is like a double bond, a triple bond, you're just looking at how many things are attached to it. So that kind of helps. But like I said, we're only going to focus on a few. So like tetrahedral, I'll have to look at my list, but probably octahedral and trigonal bipyramidal. So those are pretty common ones, but you can appreciate all the variations, right, of these kind of electron pairs, but we're not getting into all of them. but this is right our xenon tetrafluoride, so at least again you can appreciate it's square planar. I don't think I'm testing you over that, but just kind of appreciate it, know how to use it. All right, let's look at other kind of funky scenarios. So I'll either search for or reprint those common ions that we looked at, our polyatomic ions, but now we can take a look again at phosphate. And so this is good kind of practice helping us start our Lewis dot structures. So again, let's count up how many electrons we have in our system. So valence electrons, so how many does phosphorus have?
5.
5, excellent. And then oxygen,
6.
so 6, and then times 4, and so 24. And then don't forget to account for our charge. So in this case, we have a 3 minus charge. And I just like to put kind of the charge over here. So again, 3 minus, so that means we're adding 3 electrons. So now I put the 3 over there. If it was plus, then I might go minus 3. Oops. But we'll add that. So okay, 5 plus 24 plus 3. So then that gives us 32 total electrons in this system. And so now we can just start kind of drawing lines to things. And it'll probably work out. So 32 electrons, so I'm just going to put 8 around each, right? That's probably a good start. And again, we can talk about what could be better or not. All right, good. So that gives us, again, a start. And so let's learn how to analyze these structures further. And so now we're starting to look at a few things here. So, okay, one, we're appreciating that phosphorus can add more things. But let's draw what are called these resonance structures. And so, again, right, we're trying to use all these kind of oversimplified symbols and things to show complicated concepts like bonding and hybridization and ultimately like solving for quantum mechanics, right, or like back of the envelope in some ways. And so let's look at what a formal charge is. So we'll look at kind of how you calculate it, and then we'll analyze the structure, and then we'll think about this structure a little further. So formal charge is just defined as, okay, we'll take our valence electrons, like from our periodic table, right? So you look at your atom, okay, how many valence electrons? Then minus, I count the number of individual electrons. So I say number of electrons, and then minus the number of bonds. So how many like lines are attached to it. And we'll go through, like I said, this analysis together. And you might see different formulas, but they do come out to the same thing. I think this is the most straightforward way to think about it. All right, so we're looking at phosphorus. And maybe I'll write out my work here. So phosphorus, so how many valence electrons again? And then how many electrons are attached to it?
6.
So don't count, just like individual electrons, just directly attached to phosphorus.
4.
Somebody, like I said, it should be 0, right? Because you just want to count, we don't want to double count things basically, right? So when I say number of electrons, it's like individual electrons. So it should be minus 0. And then how many bonds? And so what does that give us? So 5 minus 4.
1.
So 1. And so now we can put that as our formal charge. And so the point of this formal charge analysis, there's 2 points. We're trying to see where's our electron density, but we also want to make sure that we add back up to our total charge. So let's keep going. And so looking at these oxygens, right, they're all symmetric, so we could treat them all the same. So let's look at 1. We'll do our same analysis. So how many valence electrons does oxygen have?
6.
And then how many electrons are on here? So remember, just count the individual ones first.
6.
So 6. And yeah, you're just looking one atom at a time, too. And then how many bonds?
1. Okay.
So -1. So now we have -1, right? But it's going to be -1 on all these. So that's good. So -1, -1, -1. Okay, so step 1, does that add up to -3? Well, it does, right? So we have a +1, a negative charge, that cancels, but then we have 3 minus. Okay, that's a good sign. But now here's our next hint. So when you have this positive and negative charge next to one another, you could draw what's called a resonance structure and kind of show better how perhaps the electrons are actually being shared more tightly across this bond. And so now let's look at this. And so I'm going to draw this double-headed arrow to show that this is a resonance structure. And I probably misspelled, I think that's how you spell resonance. So this is my resonance arrow there for my structure. So I'm going to draw my resonance structure. And so the way to think about this is, again, we're not going to break anything connectivity-wise. I just want to move these 2 electrons over to a double bond. So I'm going to highlight them in a different color. So, okay, circle these. So I'm just going to do that. And it doesn't matter, right? Because, again, all these oxygens are symmetric. So it wouldn't matter if you wanted to pick this one, and technically we could draw, right, 4 different resonance structures of this double bond. But now we're saying, okay, we have this like shared double bond. So this perhaps is a better representation. Again, right, you're seeing already the limitations of kind of this simplified electron counting method, and we're just trying to, again, ultimately solve the Schrodinger equation with like back of the envelope calculations. And so now we have kind of 1 double bond, 3 single bonds, but again, you could, right, draw more resonance structures. Sorry, I drew that one like super crooked. I know I'm a terrible artist, but. And okay, so now you should hopefully start thinking in your brain too that phosphorus is like an average of all these resonance structures, right? So now you could keep drawing all these where the double bond rotates. So essentially you have, and now we could say we have 1, 2, 3, 4, 5 bonds, right, shared over 4 atoms. So we have about, right, this 4/5 bond average roughly from this. Again, right, just different representations. If you'd really want to get a sense of like this bond, that's where you get a crystal structure of something, get an actual bond length, and then compare it to other phosphorus oxygen bonds and kind of see what's typical or not. But again, kind of rotate around. And then all this is also to say that phosphorus is formally hypervalent in this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we draw it like so, phosphorus technically has 10 total electrons on there. So again, technically hypervalent, violating our octet rule, but totally valid structure. All right, we may take our quick break there. So we'll come back, we'll look at probably some more hypervalent structures, and then we'll kind of practice with this, right? Because starting to get into a little bit of how do you draw these covalent structures, and then, of course, analyzing them with a formal charge. So that will be important. All right, let me go find those copies. All right, let's see how our sulfate structures are looking. So did we get total electron count on this or anything? What do we start doing so far?
Is it a total of 32?
Yeah, that sounds correct, right? Sulfur is 6, and then oxygen is 6. 6 times 4 is 24, and then 2 more. So yes.
Wait, what's the 2 more?
From the charge there from our sulfate 2 minus, so then that's telling us we have 2 extra electrons. So then I agree with the 32 count. And you could start, again, just kind of simply, right, draw a line to every oxygen, throw on our electrons and kind of see where we're at. So this would be kind of one structure. Did anybody draw something else or try something? Because I haven't put any formal charges on here. So that's kind of... So let's do our formal charge analysis and you'll see what I mean. So if we look at sulfur, right, 6 valence electrons minus 1, 2, 3, 4. So that leaves us with a 2 plus formal charge in the center. -1 on our oxygens. Again, I could do that. Sorry, I did that pretty quickly mentally. So 6 minus 1, 2, 3, 4, 5, 6 minus 1 bond. So that's how I got to -1. Plus we saw it, right? So again, kind of gets repetitive. Yeah.
So why do you count the paired up valence electrons on oxygen, but not the paired up ones on sulfur?
Well, sulfur doesn't have any anymore with how it's drawn, right? So it used up. So that's part of this, the like what's wrong with the structure type of thing, right? So I think you have the right idea in your head, maybe because you're like, okay, well, sulfur had these 2 electrons, and then, well, 2 are involved in bonding, or 4, excuse me, but then where do the other 2 go? So that's what this is showing us, is how we've drawn this structure, and I've just purely drawn it, counted up total electrons. We do have a minor discrepancy. You are kind of correct in that. But let's fix that, right? So let's just draw our other resonance structure. And so, again, right, we have a 2 plus charge next to these negative charges, so it doesn't matter which one we take. And we might as well move all of them. So I'm going to move one side and this side just to get rid of that 2 minus charge, because again, that'll fix what you see as an issue in your brain there. And so now we have, oops, sorry, I didn't want to draw it like that. So now we have our double bond to 2 oxygens. And so maybe that looks a little better, again, to your brain. So, right, going back to our Lewis dot structure of sulfur. So these 2 electrons are now involved in bonding, right, to an oxygen. Those 2 are involved in our other oxygen, and then these are involved in our single bonds. And then I'm just keeping my electrons, right? So if one of those move down, there's still 2 more. And then we still need a -2 charge, so that makes sense. This is, again, all fine. And so now sulfur, though, is formally hypervalent in the structure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So sulfur has, again, 12 total electrons. So hypervalent.
Wait, this might be a stupid question, but it looks like it's just kind of getting electrons out of nowhere.
Well, it pulled it. It has 6 electrons, right?
Because sulfur has 6.
Yeah.
Oxygen has 6.
Yeah. So they're all,
How are they double bonded?
so right, sulfur, again, how we've drawn it, maybe let's pick a different highlighter. So these two are involved with this one, let's just say. And then these two now went off with this oxygen. And right, oxygen has,
Those oxygens only have 4.
yeah, so they have 4, and then the other 2 are involved in bonding. And so that's the thing, it's like they are kind of shifting orbitals, and like we would call it, they're shifting hybridizations and stuff. And so then it throws them into different orbitals, which gives them all these pretty pictures, but that part's like beyond the scope of this course. And then let me just highlight, so then these last 2, right, are involved in those single bonds. So everybody's all accounted for, right, and has enough electrons to do the bonding. It has the orbitals to do the bonding, but like I said, that's not part of this class. So yeah, it works out 12 total electrons there.
So, would it be tetrahedral shaped even though
Good.
it's double?
Yes, exactly. So excellent conclusion. So yes, still tetrahedral, even though, right, we can change. And that's the point of, again, that cheat sheet, is the bonding doesn't matter. It just depends on how many, because, right, we can draw these resonance structures. So we're not trying to rip anything. We're not changing the geometry with these resonance structures, right? We're just showing electron movement, which would be getting into what orbitals are invoked. But like I said, we're not going there in this class. So let's try another kind of tricky one. So other expanded octets. So now let's look at some group 7 weird ones. And so see if you can make a compound. So this is always like the funny example. You could also do one of its analogs, so iodine trichloride, or II3 here. So how could you maybe arrange that? Again, get your total electron count. I'll try to finish handing out the quizzes and other paper things I have. So how did our I3s or ICL3s come out? How many total electrons did we have?
28.
Yep, 28 sounds good. And then, right, you could just start by putting iodine in the center, and then I'm just going to draw kind of 3 lines to start off with. And then, you know, if you've gotten clever already, maybe you can already see how things will go. So just kind of iodine has 7 valence electrons, so 1, 2, 3 are involved in bonding, and then that leaves us with 2 lone pairs. Otherwise, you're just trying to count it out. So if you didn't see that immediately, well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that's how you would have gotten 25, 26, 27, 28 if you didn't see that already. So that's what it should look like. And then it would be T-shaped, but like I said, we don't need to know our geometry. We're just kind of appreciating that it does indeed make these structures here. Questions about those? Oh, and I guess we should have mentioned, sorry, we should have done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or our total electron count there on iodine. So again, it's feeling 10 total electrons. And so now this brings us formally to more naming. And so again, maybe you've noticed as we've been going along that we've been using prefixes. And so now this will explain why there's a difference in naming. And so it goes from that we can't just determine what an element is. So for example, if we were trying to say like nitrogen oxide, well, there's a ton of ways that nitrogen and oxygen can combine. So, right, they have NO, NO2, N2O, 2-to-3 ratio, 2-to-4 ratio, 2-to-5 ratio. And so because it can make all these different combinations with our covalent compounds and our molecular compounds, we have to use our prefixes. And then the other kind of caveat is we're only focusing on these kind of compounds with 2 different elements, and right, we're not going down. So this quickly devolves to like organic naming, but we're just focusing on our simple molecular compounds with 2 different elements. And so then this looks pretty similar, like I said, to our other naming. So we'll still name our first element. We'll use a prefix if we need it. So if it's not something other than 1. And then we have to use a prefix for our second element. So like carbon monoxide, right? So you don't say monocarbon monooxide, but you do this second mono always. So carbon monoxide. And again, I'm pretty forgiving on the spelling, since it can be confusing with the prefixes, adding the prefix in there. And so again, just your standard prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, and then again, right, it can go on and on and on, especially for organic chemistry. And so like we mentioned, if we have 1 atom in our first element, we usually omit the first mono. All right, so see if you can name those. So take a second, try to come up with their name, and then we'll go over them as a group. All right, let's see what we got. So what did we get for the first one? Yeah, so then it'd be so yeah, nitrogen, and then yeah, triiodide. So again, looks kind of funny there. What about for B here?
It would be like phosphorus pentachloride.
Yep, excellent. So phosphorus pentachloride. Good. And then what about this one?
Can you scroll up? Go to the tetra.
So then, yeah, put it together. So tetraphosphorus. And then do we deca, and then, yeah, sulfide. Yeah, excellent. And so hopefully you could find covalent naming easier. Again, since it's the prefixes, so it's kind of, should be easier. I'll talk about one of the weird ones now. So let's go back to aluminum. So hopefully I won't test you on aluminum chloride. That being said, it could have slipped in somewhere. So let's go look at aluminum chloride real quick. And so this is kind of a funny compound. So we probably treated it like an inorganic compound, and that is perfectly fine to treat it as an inorganic salt for this class. But there's a lot of discrepancies with aluminum, and that's because its true structure is this. And so it's actually even weirder. Normally we just treat it as this 3 coordinate in the gas phase. Let's see if I can find. Oh, yeah, here it is, right? So it's shown as the monomer. So at the gas phase, it's this trigonal planar complex, which is even more confusing. So it is a covalent compound when you actually analyze it, which is, again, kind of unexpected. And then it is really this weird, like, 6 coordinate, or this dimer species. That being said, I'm just trying to show you that you'll see different naming for aluminum chloride, which is why I'm going to hopefully not test you on it. I'm sure I'll forget. But there will be discrepancies. So you might see aluminum 3 chloride, you might see aluminum chloride, you might see aluminum trichloride, and that is why there is so much confusion around it. Is, again, right, you assume it's an inorganic compound. That's how we learned it. That's how we're going to treat it in this class for the most part, except we actually are going to say, hey, it is a covalent compound. So kind of confusing. And beryllium chloride is the same issue, where we treat it, we name it as an ionic, but it's really a covalent, so it's kind of confusing. All right, other things to just kind of clarify and make sure we're all on the same page on is, well, now we can find our formula mass or molecular mass of our compound. And so technically speaking, our molecular mass is going to be defined as our mole of our compound. So it's going to be grams per mole. And we haven't quite defined what a mole is. I think some people have shouted out what it is, but it's basically a macroscopic amount that we can see. But the whole point of our molecular mass or our atomic mass, so looking at our just one singular molecule, is that they come out the same, whether we do it in our grams per mole or atomic mass unit. And that goes back to how the mole was defined. And so let's, again, look at it. So pulling up P table for a second. So, that is not what I wanted to do. So going through water, again, just kind of starting simply. So we look at our periodic table, we have this 15.99. So that is, again, both for one atom or 1 gram per mole. And then the nice thing is, well, we can add up all these numbers. So again, I would have picked like 15.99. That's fine. Small discrepancies are fine. I expect that. But again, you add it all up and you either get 18.0 atomic mass units, again for 1 molecule of this, or we can also say, hey, this was 18 grams per mole for water. So once we're looking at our larger unit. And so the conversion factor between this is Avogadro's number, but I'm probably not going to prove it to you right now because, again, 100 level Gen Chem, trying to keep it at least somewhat easy. And so that's kind of nice. So let's practice with another one. We'll do my favorite here, silicon tetrachloride. So see if you can get right the atomic mass. So what does that mean if we're just looking at like one unit, or what if we're looking at its molecular mass? So just take a second to add that up. So that sounds correct. So let's go through it together for everybody. So sorry, let me get my P table back up. And so again, just so we're all on the same page, so we got about 28 for silicon. Again, try to use as many digits as you can, but also trying to be reasonable. Okay, so we have silicon plus our 4 chlorines, right, from our subscript. So we need 4 of them. And so that's like 35.45, so times 4. And what did you say about 69.9 you said, correct?
169.898.
So 169.898 or something like that. So again, depending exactly what numbers you pick. So yeah, and again, that's going to be atomic mass units for 1 molecule of that, or again, the whole point of the periodic table is that it's set up to work for both. So 169.898 grams per mole there. Excellent, not too bad. Let's do another slightly harder one. So now let's do aspirin. And so the formula is C9H8O4. So just practice adding that up. let's see how we're doing. So we have carbon. I'll kind of just punch it in. So about 12.011, and then we said there were 9 of them. Oops. So times 9 plus 1.008 for hydrogen roughly times 8 plus, again, you can use 15.999 or 16, either way. So what do we get for our molecular weight of aspirin? So I see some nods, so I assume everybody got 180, and what do I get? 0.159. And again, that's grams per mole, or AMU if we're just looking at one molecule. That looks pretty good. I guess we can start going through our molecular geometry, at least for our last few minutes of class. So again, we're just kind of re-emphasizing which ones we need to know, because we don't need to know all of them. So we have our trigonal planar, so that's going to be like boron trifluoride here. So kind of typical compound, or aluminum trichloride like we just went over. Something else that could have the structure would again be anything that has 3 things bonded to it. So now I'll draw out acetone here. So carbon, right, has 1 thing in the center, is bonded to 1, 2, 3 things. So ignoring the double bond, so still takes that, again, trigonal planar shape there. Oh, and then other things to note. So this is why boron is, again, an area of good research interest. So it does make these compounds. So again, 3 valence electrons, right? So only 3 are available for bonding. But what's kind of the issue here with boron? How many total electrons does it have?
6.
So 6. And so, of course, right, that does not satisfy the octet rule. So only 6 total electrons on boron. And so that makes it reactive. Typically, it wants to make like oxygen bonds in and have oxygen donate electrons to it. And, of course, make it satisfy the octet rule. And so boron, again, these compounds. So boron trifluoride is a fuming angry liquid, as, again, it reacts with water and oxygen. All right, tetrahedral. So what was our classic compound? Do we remember? Went over. Diamond's a good one, so I like that. So I was going to go with methane here, but I'll put diamond because that's also a good tetrahedral classic structure there. I was just thinking of more like discrete molecule like methane, but again, diamond is repeating tetrahedral units, so giving it its strength. And again, I'll rewrite silicon tetrachloride.
Is that why diamond is so strong?
Yeah. So yeah, that exactly goes back to the strength and the properties. So now you're starting to put everything together, right? Which is what we want you to be doing. And again, you could go crazy drawing out all these. So carbon tetrachloride, so that was a famous solvent. It's carcinogenic, so it's been dropped. And then obviously there's bromine forms, germanium, again, all these compounds. Some of these germanium compounds are solids because they get heavier. Or tin. Although we'd probably include these in kind of our ionic compounds. And then trigonal pyramidal. Sorry, I don't want to go too fast. Let me copy that. And then, do we remember what trigonal pyramidal compound we mentioned earlier? One of those small molecules. So I'll give it away.
Phosphorus, the tetrachloride?
Or
Or
trichloride.
trichloride.
Yeah, that's a good one. So phosphorus trichloride. So good. So those group 5, or the one that I was thinking of again in group 5 would be our ammonia. But any of those. So just have those in your brain. Excellent. So trigonal pyramidal, again, right, looks like a pyramid. Lone pair not included in geometry. And then the last one we have to know is bent. And so like I kind of teased with your compound chem, there's actually 2 bent geometries, but in this class we're not going to make the distinction between them. So we have our classic water bent. And so this is usually just always called bent. And then the other example of bent is SO2. And so I'll draw out the Lewis dot structure since we're kind of running low on our official class time. And so if you look back to your compound chem sheet, right, this starts off with group 3. So 1 lone pair, 2 things. But then now we're missing one of those substituents. And so technically this is called V-shaped bent. But again, we're not making the distinction. So they have different angles, which I would refer to the compound chem sheet for those different angles. So right, you could pull up the angle here. Oh, sorry, went the wrong way. And so our 3 electron pair has about a 119 degree angle between these two versus our tetrahedral bent, which is going to be closer to 104.5. So slightly different, but like I said, not important in this class. You can just kind of take that for your information. But as long as you can identify either one of these as bent, that's all we need to take in this class. And then we'll finish up Wednesday with looking at polar molecules and trying to interpret these organic structures. And questions?
When for molecular mass, when you're starting to involve isotopes, how do you figure out what like carbon 13 is going to be compared to? Like, how do you know it's a carbon 13 in the molecular mass formula?
Oh, so for the molecular mass, you just take the average. So that's why you just take like the average mass on there. But to your point, so it'd be pretty hard to identify like a C13 by like mass spectrometry, but you would be able to identify, and I could, pull up some examples, but bromine, for example, is one of those, right, with 50-50 split. So in mass spec, it gives a very distinct pattern. And then that's where computers are kind of more useful, is so what ChemDraw will do, or like these fancy chem programs, is that they'll tell you like what your different isotopic relative things are. So like your most abundant peak should be blah.
And then I should just do this week and last week on Blackboard.
Probably, yeah. I'll try to throw together maybe something, but I don't want to make promises I can't keep there for you. But yeah, so you get these like splitting. So this is chlorine, actually. Let's try to find, there we go. So this is an example, right? You shoot this compound down the mass spec, but like you were saying, okay, well, bromine has 2 isotopes. So you would see it in this classic isotopic splitting pattern where half are at a mass of 79, half are at 81. But like I said, we're just doing the average in this class. But yeah, that's great that you're thinking about that. And so chlorine and bromine have pretty distinct like splitting patterns. So that's like helpful for mass spec. But otherwise, then you need the computers to like help you with like the correct peak matching to isotopic ratios. Yeah. Yeah, really good question. All right, I'm going to end the stream unless there are other questions.